Nej, tror jag start.
Okay, so today we're having the second lecture in the proof complexity as a computational lens course. We're going to start with slides, and then we're going to continue and spend most of today on the board. And so today we're going to have a more theoretical take on proof complexity, and this is our focus for the rest of the course. We had a lot of applications and motivations driven by applications, and we designed proof systems last lecture to capture exactly what algorithms are doing. Now we're taking a step back and thinking about what is actually a proof. So, and that is a good question. Like mathematically speaking, we write proofs all the time, but it's a relevant question to ask, what do we actually mean? Can we give a precise definition of what a mathematical proof is? And this is what we're going to talk about today, and then throughout the course. We need to pin down what we mean by proof, and then we'll talk about what kind of logical statements can we prove efficiently, can we find such proofs constructively, what kind of methods of reasoning should we consider, and when we're saying that we want good proofs, how would we measure this in a mathematically quantifiable way? And if there are different measures for proofs, can we relate them in some way? This is what this course is going to be about. And as I already said, we are going to switch gears a bit. I'm going to do theory today, not so much applied motivations, but more theoretical considerations. And there's going to be some basic definitions, some recap of what I said last time. And then we're going to do our first lower bound. We're going to talk, like a complete spoiler alert, we're going to talk about the resolution proof system and prove that resolution cannot count, that proving the pigeonhole principle efficiently is something that resolution cannot do. And I plan to go pretty fast in the beginning because some of this we covered last time and all of it will be online. And so if you feel it's too fast, you can recap later. So let's talk about what a proof is. For instance, if I'm telling you that 25,957 is a product of two primes, what would you buy as a proof of this fact? And now you should think of, obviously, this is small enough that you'll be able to brute force it, but it's worth thinking about, like, suppose that this would now be a number with, 10 digits or 100 digits. What would you consider to be a proof of that this number is a product of two primes? The first thing we can always do, and that I will hopefully do liberally during this course, is a proof by intimidation, that you should really be able to figure this out. Okay? We're not going to buy this. This is not a proof for us, because it didn't help me. I already see the statement. The proof should somehow help me to actually verify why the statement is true. Now I can go overboard and do something else. I can just take and compute the remainder modulo 2 and then modulo all odd numbers smaller than 25,957 and compute and list all the remainders. And now you will see that all remainders are non-zero, except that here for 101, we get remainder 0. From 257, we get remainder 0. Everywhere else, we will see remainder non-zero. And this proves that these two numbers are the divisors and they have to be prime. Okay? So this we will accept as a proof. But this seems a little bit verbose for us to be a proof. So this is an acceptable proof, but we don't like it. The question is, can we do better? And here is something that I would argue is a much nicer proof. I just say, well, 25,957 is 101 times 257. Just check this and convince yourself that these two numbers are prime. And now this we will accept as a proof. Why? Because given this information, I can actually in polynomial time verify the correctness of the claim. We know how to check prime numbers in polynomial time. We know how to multiply in polynomial time. So before it wasn't clear how to check this claim, but now, thanks to this additional information, the claim at the top of the slide is now a polynomial time verifiable statement. And this is what we mean by a proof. And this is the simple but crucial insight that Cook and Rekau had back in 1979 when they defined what a proof system is and started the research area of proof complexity. So what we'll see here is not exactly their definition, it's an adaptation of their definition, but it's more or less the same. So by a proof system, I mean any algorithm with two arguments, which I'll denote x and pi. It should run in polynomial time in the total size of the inputs. And it should have the property, this is a proof system for a language of strings L. If for every x in the language, there is some pi that when I feed my algorithm, my proof checker, we can think of it as a proof checker, x and pi, the algorithm will say yes, it will output 1. So it will, given pi, the algorithm will say that yes, I believe that x is in the language. Obviously, if I gave some, proof pi prime that was buggy, then maybe the proof checker says, no, I don't believe you, this is a buggy proof. But there should be one proof that makes the proof checker, the algorithm, accept x. However, if x is not in the language, then regardless of what pi I get, the checker should always say no. And again, the algorithm should run in polynomial time in the total size of the inputs. This is what we mean by a proof system. And the important thing here, which I already said twice, is that the running time should be polynomial in the total size of the input. So not in x, not in the claim x to be proven, but in the my checking time also grows with the proof. So it could be that I have a humongously large proof pi, and then I have more time. But I should be polynomial in the total size of the input. And now a propositional proof system, what we're going to study in this course, except we're going to switch gears in a few slides. But for now, we'll stick with tautologies to say that a propositional proof system is a proof system for the language consisting of all valid propositional logic formulas that are true regardless of how you assign the variables. Okay, and just to make sure we're on the same page, so we have Boolean variables ranging over false and true, 0 or 1. And then we can think of standard connectives, negation, conjunction, disjunction, implication, and equivalence. And then we just define the set of well-formed propositional logic formulas, as I think you've seen in your introductory course in logic. And then we can define that's the syntax, and then the semantics is that, well, we can define, any assignment alpha assigns values to the variables, and then we extend it in the natural way from subformulas to formulas containing these subformulas. And again, I'm kind of going a bit fast because I think we know all of this. I'm just making sure that we agree on the terminology. We say that the formula is satisfiable if there is an assignment that makes the formula evaluate to true. It's valid if all assignments makes it evaluate to true. It's falsifiable if there is an assignment that makes the formula false, and it's contradictory or unsatisfiable if no truth value assignment satisfies the formula. Okay, and here is our first, the most simple proof system you can think of is just write down the truth table. And note that this is a propositional proof system, because if I get the truth table for a function, for a formula, I can certainly go over it and in polynomial time check that this truth table is correct. And so the question is then, do we like this? And I think you probably agree with me that somehow this doesn't seem to be the proof system we're after. So we need to make more precise why we don't like truth table as a proof system. And the reason is that we want proof systems ideally to be concise. So given a proof system such as truth tables or the proof systems...
There is a question in chat.
Yes?
If there's no restriction in the size of pi, can pi just be the entire accepting computation history of an NTM that accepts x?
For instance, yes. That would be a perfectly valid proof. And now you already realize that we are going to be able to make connections to NP and co-NP here, right? Because anything that is indeed like, in fact, you don't, the only thing I would need if I have a non-deterministic Turing machine, then you can actually hardwire the non-deterministic Turing machine into the proof checker, and I just need to know the non-deterministic choices, for instance, right? Good, thank you. Please interrupt if you have questions. So the complexity of a proof system is the function such that if x is in the language, then there is a proof of size at most g of the size of x. We say that then g is the complexity of the proof system. And what we're looking for now are, it's clear that the smaller the function g is, the more efficient the proof system is. And in particular, we're interested in polynomially bounded proof systems where proofs scale polynomially with the size of the input. And the reason we don't like truth tables is obviously that they have exponential scaling in the input size, not polynomial scaling. And now something that was an insight back in 1979, but is kind of blindingly obvious to us today because of the way we define these complexity classes today, is that NP is equal to co-NP. So the class of non-deterministic polynomial time-solvable problems is closed under complementation if and only if there exists a polynomially bounded proof system for propositional logic. And I'll do this very quickly, but because basically it's almost by definition, you realize that NP, the way we've set things up, NP is exactly the set of languages that have polynomially bounded proof systems, because the NP verifier is the proof checker. And notice that our definition of a proof system was exactly the one for NP. The only thing that was missing is the polynomial bound on the certificate size. So a proof checker with a polynomial guarantee on the size of proofs is exactly NP. So that means that, and now we see that, well, the language of tautological formulas is in co-NP. And so if NP is in co-NP, then by definition, clearly there is a polynomially bounded proof system for the language of tautologies. And in the other direction, well, if there is a polynomially bounded proof system for the language of tautologies, then notice that the language of tautologies is complete for co-NP. So I can reduce anything in co-NP to tautologies, and tautologies is in NP, so hence anything in co-NP is in NP. And I'm doing this a little bit quickly, but really there's nothing going on here. We're just shifting definitions around. Okay? So, of course, we believe that NP is distinct from co-NP. We have no idea how to prove it. Note that this is a harder question, potentially, than P versus NP, because if we could separate P, NP, and co-NP, then P not equal to NP would immediately follow as a corollary, because NP wouldn't be closed under complementation, but polynomial time is clearly closed under complementation. However, it is perfectly conceivable, if perhaps unlikely, but what do we know, that P would be distinct from NP, but NP is still closed under complementation. But the reason for proof complexity and the argument, arguably, why Cook and Reckhouse started the study of proof complexity was to try to separate P and NP by separating NP and co-NP, by studying stronger and stronger proof systems, until one beautiful day we developed techniques where we can approach any proof system as defined by this polynomial time binary certificate. And we should do this for stronger and stronger proof systems and try to get there. What do we mean by stronger proof systems? So another notion that is important to know is that of P simulation or polynomial simulation. We say that proof system P1 simulates P2 polynomially if there exists a polynomial time computable function that translates P2 proofs into P1 proofs. Okay, so for any proof pi that makes P2 accept an input f, say, we just apply the translation lowercase f and get a P1 proof, and this translation function should be computable in polynomial time. Note that this is just a standard reduction, that we're used to from the theory of NP completeness. We say that there's a weak polynomial simulation or P simulation if we don't know of such an explicit translation function, but it is true that the smallest P1 proof scales polynomially with the size of the smallest P2. Okay, and given this, now this creates some kind of relation, and you can compare proof systems with respect to whether they simulate each other polynomially or not. And in particular, if two proof systems polynomially simulate each other, then we say that they're equivalent. From the point of view of theory, once we have a P simulation, we don't distinguish between the two proof systems any longer. Notice that in practice, there could be a bad polynomial blow-up that is really important, but in theory, we won't care. So anything we're only shooting for, anything that only differs by polynomial, we mostly won't pay any attention. And obviously, if a proof system P1 simulates another one, but we can prove that the other proof system does not simulate the first one, then we've shown that the first system is strictly stronger than the other. How would we show this? Well, we show that P1 simulate P2, and then we'll somehow find a family of formulas for which the P2 proofs scale faster than polynomially, whereas the P1 proofs scale polynomially. That would establish that P1 is a strictly stronger proof system than P2. And we'll see such results in this course. Talking briefly about also what we had, what we talked about during the first lecture. The constructive version of this problem is given a propositional logic formula to decide whether it is a tautology or not. And this is, in fact, the problem that motivated Cook and Levin when they defined NP completeness. And this problem was studied well before NP completeness. In particular, if you go to Dick Lipton's blog, you can read the letter Gödel sent to von Neumann, recommended read, where they discuss, I mean, obviously the terminology of NP completeness was not around, but it's very clear from the letter that they realized that the question of whether it's possible to efficiently determine whether a formula is a tautology or not is a very important scientific question. And in fact, these days, since the turn of the millennium, this is one of the 7 millennium problems in all of modern mathematics. We believe that this problem is exponentially hard to solve. Practitioners don't care so much. They built amazing SAT solvers, as we saw last time, that are used for a lot of different applications in industry, for huge propositional logic formulas with hundreds of thousands or millions of variables. But at the same time, we can also, if we're evil, we can cook up propositional logic formulas with just around 100 variables that you can't even crack with the access to a supercomputer. And so one other reason for doing proof complexity, more applied reason for proof complexity, is to study algorithms for solving propositional logic formulas, model them as proof system, and try to prove upper and lower bounds for the proof systems modeling these algorithms, and in doing so, trying to understand how these algorithms work. And we will not return to this one. We talked about it at some length, this discussion, this comparison between algorithms on the one hand and proof systems on the other. We talked about it during the first lecture, but we won't revisit the question anymore in this course. And I should say also that from a mathematical point of view, I would argue that this is maybe the most important application area of proof complexity today. Because this first program, proof complexity, has a way of separating NP and co-NP, as happens for other approaches such as circuit complexity. Pretty early on, researchers got hopelessly stuck, and I would argue that we've been stuck basically since the 80s. There are long-standing open problems that we have no idea how to solve, and there's very little hope of being able to develop techniques to deal with fully general proof systems. Here, developing our proof complexity tools well enough to actually understand real-world algorithms is something that is within reach. But the not-so-nice thing is that if you really want to model real-world algorithms, then reality tends to be messy. And if you want to be really faithful, then you don't get these clean, beautiful models that we like to do math with. And it kind of gets messy, and you need to get your hands really dirty. And it's not to everybody's liking, because a lot of us do mathematics because we like clean, beautiful mathematics. So I think this is maybe one reason why not so much proof complexity has been done about this. And we are going to keep our hands mostly clean during this course. So I don't think we'll return to this question again, except for one interesting question, which is the question of efficient proof search, because that can be modeled nicely. So suppose I have a proof system P, let's fix it. A proof search algorithm, A sub P, is a deterministic algorithm that takes as an input the formula F and outputs either a proof that F is a tautology or reports that F is not a tautology, that is falsified. And now there's the concept of automatability. And I see it says automatizability here, which is a typo. We should change it. These days, the modern term is automatability. We say that a proof system is automatable if there exists an efficient proof search algorithm. What does this mean? Well, efficiency, obviously, if you're going to output a P proof and the shortest P proof is exponential, then you can't be very efficient. So it's fair to measure efficiency in terms of the best case scenario. So, and if we consider a proof search algorithm to be efficient, if it runs in polynomial time in the smallest possible proof. Right. Okay. If that is the case, if there is such an algorithm for a proof system P, we say that the proof system is automatable. Okay, and technically speaking, you have to be a little bit careful. The algorithm should run in time polynomial in the size of the formula plus the size of the largest proof, but I won't go into those. So now, looking at truth tables again, it is trivially automatizable because basically we're just padding to get exponential time. So we don't even need to look at the proof, we can just brute force. Okay? So when we're talking about automatability, we want proof systems that are not only automatable, but that are strong, so that you can search for proofs, but there are concise proofs to be found. So the sweet spot would be to find a proof system that is strong and also automatable. However, it seems that this is not possible unless P is equal to NP for resolution and for many other proof systems. And this is something that we hope to talk about towards the end of the course. However, as I told you, this is a worst case result. So it's hard to find, unless P is equal to NP, you cannot find the algorithm that always successfully searches for resolution proofs in polynomial time. But of course, we know that SAT solvers do this very successfully in practice. But there are no worst case guarantees. The third reason that to do proof complexity that we will be somewhat interested in is that what we will do when we study different proof systems is we'll look at different types of mathematical theorems or combinatorial principles, such as the pigeonhole principle, handshaking lemma, or other principles, and then try to understand how hard is it for a given proof system to prove that this principle is valid. And if we can find different combinatorial principles that are hard or easy for different kinds of proof systems, modeling different kinds of mathematical reasoning, then that gives us a way of quantifying, in a sense, how deep different types of mathematical truths are. If you really want to go hardcore into this area, then you should do something that's called bounded arithmetic, which is more into logic. We won't do anything of that, but we will talk about a number of different combinatorial principles, and we will study different syntactic, algebraic, geometric proof systems and try to understand how efficiently or not these different proof systems can reason about different combinatorial principles. Up until now, we talked about tautologies only. If you remember from the first lecture, I actually defined proof complexity differently. I defined it as proofs for unsatisfiable CNF formulas. So what's the connection? Well, if you have any formula F over any standard connectives, you can convert it to a formula in conjunctive normal form that is only linearly larger and is such that the CNF formula is unsatisfiable if and only if the original formula is a tautology. And this goes back to Zetin. This is a so-called Zetin transformation, where basically what you do is you look at all the subformulas, you introduce a variable for every subformula, and then you write down clauses enforcing that all subformulas are computed correctly. Okay, so for instance, if G is the subformula H1 or H2, then I introduce three variables x sub G, x sub H1, x sub H2, and then these three clauses will force G to be correctly computed given H1 and H2. Namely, if G is true, so that not XG is false, then either XH1 or XH2 has to be true. But if G is false, so XG is false, then that forces both H1 and H2 to be false. And similarly, you can do it that we also have implication on this slide, and it's not hard to do similar translations for and for equivalence. So you do this for your whole formula in a bottom-up fashion. And then you just add a unit clause, a clause with a single literal that says not xf, where f is the whole formula. Okay? So now suppose that f is a tautology, then all the clauses will force all subformulas to be computed correctly, so that xf has to be true because f is a tautology, but we've added a unit clause saying that xf has to be false. So if f is a tautology, then this CNF formula is unsatisfied. And the other way around. Okay, does this make sense? This is kind of a, again, I'm doing this a little bit fast, but this is a standard translation. So this means that we can actually say, actually, I'm only going to do proof systems for formulas in conjunctive normal form, and I can consider this to be a general proof system if I like, because I can take any formula and just translate it to CNF and then run my CNF-based proof system. And that is what we'll do from now on. So now we're back to where we started in lecture 1. From now on, we're only going to talk about formulas in conjunctive normal form, and we're only going to do proof of unsatisfiability. And all of the notions we had, automatability and everything, now carries over, but we will not discuss proofs of tautologies, but proofs of unsatisfiable forms and contradictions. So one reason for mentioning this is if you read the proof complexity literature, you will see that researchers have been slightly damaged by this sort of dual view of things. So it's proof complexity is a slightly schizophrenic area. It would be perfectly normal, for instance, to refer to an unsatisfiable formula as a tautology. Okay? You will see this in the literature. Now, here's a tautological CNF formula, and what they mean, the authors, is that actually there are no satisfying assignments. And also we talk about proofs for formulas where we actually mean proofs of unsatisfiability of these formulas. So during this course, I'm not mature enough to refer to an unsatisfiable formula as a tautology. I'm not yet reached that level of enlightenment, so I won't do that in this course. But what I will do, and I should warn you about this, that when talking about a proof, or a proof by contradiction, or a tautology, or a refutation, those will be the same throughout this course. So a proof is always a refutation, pretty much, unless stated otherwise. Right. So now we gave a very generic definition of proof systems before. In most proof systems that you see out there in the real world, they actually are typically a sequence of derivation steps. So let me formally define a proof system to be sequential if it's a sequence of lines of some syntactic form, and then every line is inferred from previous lines by some kind of inference rules. Note that there's nothing in the general definition that says a proof system has to be sequential. Our general definition just said that P is a polynomial time computable binary predicate, but most of the proof systems we will study will be these kind of sequential proof systems. In particular, we'll study resolution. So let us remind ourselves what resolution is. We saw it briefly last time. So the lines in a resolution refutation are disjunctive clauses. There's only a single rule for inferring new clauses, namely the resolution rule that says that if I previously inferred B or X and C or not X, then I can resolve over X and infer B or C. And I will refer to B or C as the resolvent of B of X and C or not X. And now, importantly, I will view all clauses as sets of literals, so order is not important, and there are no repetitions. Okay, throughout this course, a clause is a set of literals, And actually, I will also think about the CNF formula as a set of clauses. So we never have multiple copies. We'll be relaxed about this. So a resolution derivation, which will always be a lowercase pi from a CNF formula f, it starts with some clauses in f, and then you can add new clauses by the resolution rule. And if the final clause in the resolution derivation is a, then we say that pi is a derivation of a, and we'll use this in notation, say that pi colon f v dash a. Say that pi derives the clause a from f. And we'll also use this notation for other proof systems. Now, something that I won't prove to you, I'll just prove it by intimidation, is that resolution is sound. That is, if I can derive a clause from a formula, then in particular that clause is semantically implied, meaning any satisfying assignment to all the clauses in f also has to satisfy a. And that is not so hard. It is basically by induction over a derivation, because the resolution rule is sound. Slightly harder, but not too hard, is to prove that resolution is complete, meaning if actually a CNF formula f does imply a clause a, then I can derive by resolution either a or some strictly stronger clause a prime that is a subclause of a, that contains some but not all literals of a. This is not hard, but I won't do this proof. But in particular, what we will use is that if from a formula f I can derive the empty clause containing no literals, which we denote bottom, then that shows that the formula is unsatisfiable, and vice versa. If f is unsatisfiable, then it always has a resolution derivation. So a resolution refutation, let's see it. We have here an example formula consisting of 5 clauses. So we can start the refutation with these clauses. And then from, for instance, clauses 2 and 4, we can resolve them over z to derive x or not y. We can then resolve clauses 1 and 6 over y to derive x. So far we've proven that if this formula is satisfiable, then x has to be true. But then we resolve clauses 3 and 5 over z and derive that no, any satisfying assignment to the formula actually has to satisfy not x, has to falsify x. And now we can resolve clauses 7 and 8 and derive contradiction. And in general, you can view a resolution refutation in 2 ways, either just as a sequence of clauses, but we will more often think of the resolution refutation as also coming with these annotations. So like specifying, no, this is an input formula, and for every non-input formula, we'll specify how it was derived. Okay, so I will think of, and this also goes for other proof systems, we'll think of the lines in a proof as coming with annotations. Note that this is not necessary in order to make resolution into a proof system, because if you know that something is not in the formula, then you can just basically search exhaustively for any 2 previous clauses that could be resolved to yield this formula. But the nice thing with this definition is that it will also tell us something about the structure of the formula. In particular, we can view then a resolution refutation both as an annotated list or as a directed acyclic graph, or DAG.
Yeah, we got another question.
Yes.
So do we have similar results for other rules of interference? Like, can we work with a proof system with some other inference rule and still have completeness and soundness?
There are many different proof systems. We'll see a few in this course. Yes. Yeah. And typically, like any proof system you study, in particular, if you go back to the proof systems we studied in the introductory lecture, where we saw resolution, we saw Nordström sets, we saw polynomial calculus, cutting planes, Reilly-Adams, sums of squares, stabbing planes. What else did we see? We saw extended resolution. I didn't emphasize it, but all of these are complete. Like pretty much any proof system that you want to study should have this completeness book. Okay. And for resolution proofs and also for many other proof systems, we'll typically study sequential proof systems, and we can view them as sequence of lines derived, or we can view them as graphs. And I will often switch back and forth between the proof as a list of lines or as endowed with a directed acyclic graph structure, and just go back and forth between the 2. And in particular, if the DAG is a tree, which I think is the case here, so all nodes have out degree 1, then we talk about a tree-like refutation. Okay, so this particular refutation is tree-like. Let's recall some measures that I think we maybe talked about in the introductory lecture also. The length of a resolution refutation is the number of clauses. In this case, we have 9 clauses, so the length is 9. The size should typically, strictly speaking, we should count something like the total number of literals in the resolution refutation without counting repetitions. But there's only a linear factor difference between this and the length. So actually, for resolution, we just define the size to be the length, because I don't care about this linear factor. And counting the number of clauses is a nicer measure. For other proof systems, there will be a difference. We'll get to that. For instance, for polynomial calculus and for cutting planes, we do care about the difference between length and size. For resolution, I'll be very relaxed and I'll just say length and size and I'll mean the same. And this is what we're mainly interested in this course. But there are also other definitions of other proof complexity measures. I mentioned space in the introductory lecture. So let me quickly define it by example. There are 2 measures that we care about, clause space and total space for resolution. And clause space is basically given the DAG structure. The clause space at the step T in the proof, at step 7 in the proof, is the number of clauses before or at line 7 that are used afterwards. To see this, look at the DAG structure, and you see that the clause at line 7, I always need to keep at time 7. And then you see that all of these highlighted clauses here in red are actually used at step 7 or will be used later. So you have to keep them in memory. So the clause space usage or the line space usage at time step 7 is 5. Total space would also count the number of literals. So apparently now you get 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now to define the space of a proof, you just go over all the steps and take the max. Okay? So this is how space is defined. And now, once you have size or clause space or total space, we will also consider other measures. You can define the size of the refuting a formula as minimizing over all resolution refutations of F and taking the smallest one. And similarly, you can think of the clause space of refuting F as being the minimum clause space of any refutation, and similarly for total space. And just to make a final connection back to algorithms, size bounds for a proof system are interesting because they give lower bounds on running time. Space bounds give lower bounds on memory consumption, and size-space trade-offs actually measure what can happen if you try to optimize running time and memory usage at the same time, which is something that modern algorithms typically try to do very aggressively. Okay, so we're almost done, and we're about to switch to the board. How do we prove size lower bounds or length lower bounds for resolution? So the recipe is basically we design some kind of nice family of CNF formulas that have polynomially scaling size typically. And then we just need to show in resolution or in our favorite proof system P that the smallest refutations, their size scales super polynomially. And we have a super polynomial lower bound. The question is, how do you prove? Proving the existence of a refutation is you design one. But to prove the non-existence, that is typically very challenging because you have to prove that regardless of what crazy derivation steps you do, it can never lead to a short refutation. This is typically very, very challenging. And in order to be able to argue this, we can typically only do it for formulas that we understand really, really well. Because in order to prove lower bounds for a formula, we have to have an intimate understanding of what the formula encodes. And so we have this slightly paradoxical state of affairs that typically formulas that we're able to prove lower bounds for are also formulas that we understand very well and that therefore seem very easy. And this is not, this is a common theme for much of computational complexity, not only proof complexity. That typically what we're able to prove lower bounds for are simple things because they need to be simple in order for us to understand them so that we can prove lower. And in particular, the one simple formula that we'll study today, we'll switch to the board soon, is the pigeonhole principle formula, which is maybe one of the simplest principles you could think about. Namely, the principle that says that n+1 pigeons don't fit into n holes if every pigeon wants its own hole, except we want to do resolution reputations, so we'll write it down as a contradictory CNF formula that says that there is such a mapping. Okay, so we define variables p, I, j that say that pigeon I goes into hole j, and then we say for every pigeon I we have a clause that says that pigeon I gets one of the holes, hole from 1 up to n. And then for every hole j and every pair of pigeons I and I prime, there's a clause saying that it's not the case that both I and I prime go into hole j. Already this is unsatisfiable. If we want to, we can encode a stronger pigeonhole principle by saying that every pigeon should get exactly one hole, so no pigeon I should fly into two distinct holes j and j prime. We can also consider the onto pigeonhole principle that says that every hole j gets at least one pigeon. All of these versions are dead hard for resolution. Okay. We will focus on the vanilla pigeonhole principle consisting of just these two classes of formulas and prove a exponential lower bound for resolution. So this is a result by Armin Haken. This is arguably the result that really got proof complexity started. I mean, proof complexity was defined by Cook and Reckau in 1979, but the first monumental breakthrough result was Haken's lower bound in 1985, which was then followed by other breakthroughs for other formulas that we'll also talk about later in the course. We won't do Haken's proof, however, we will follow a nice exposition by Pavel Pudlak, and this is what we'll do now. So we'll switch to the board, and just to say that these slides will be online, all the references that I flashed are at the end of the slides, as you can see here. So I think this is a good time to take a break and switch to the board. Before we break, are there any questions at this point from the virtual audience or physical audience? Okay, otherwise let's hit the pause button and take a break. Okay, so now we're switching to the board. There was one question first. So if we're proving lower bounds for the pigeonhole principle, will those lower bounds be in terms of the size of the encoding, and could we envision having different bounds or different encodings? The answer is very much yes. In particular, already in CNF, we've seen now what I showed in the slides. We had different encodings, like we had the vanilla encoding, the functional encoding, the onto encoding, the functional onto encoding. There are also other types of encodings. So the encoding we have now is that we have variables. Well, I switched now from p to x because that's what my notes say. So we have variables xij, which we think of as saying that pigeon I flies into hole j. We could also think of having variables encoding a bit string and a formula that says, so for every pigeon there are basically log n bits saying which hole the pigeons fly to, and then we can say that no two pigeons are allowed to collide. That's the binary pigeonhole principle. We could also, the formula here is saying that every pigeon gets a free choice of all holes. There are also more restricted versions of so-called graph pigeonhole principles, where you give a restricted choice, say every pigeon has only maybe 5 different holes to choose between, or something like this. There's like a rich variety of different pigeonhole principle encodings. In fact, this is, I say by a mile, the most studied formula family in all of proof complexity. Proof complexity theorists obsess about the pigeonhole principle formula. Alexander Razborov has an entire survey written exclusively about the results about the pigeonhole principle formula. It's from 2002. It's a little bit dated because it's for the simple reason that it's over 2 decades old, so some progress has been made, but actually not too much. And so Razborov's survey is still extremely readable. What we will focus on today is the vanilla pigeonhole principle formula, Again, that says just every pigeon. So pi says that pigeon I gets one of the holes. J goes from 1 to n. We have m pigeons and n holes. We have m larger than n. And then for every pigeons I and I prime and j, we have a whole axiom that says that either I does not fly into j or I prime does not fly into j. And we'll be slightly relaxed about notation in this and future lectures. So I write I strictly less than I prime contained in M means what you believe it means, namely that I and I prime both live in M, but I is smaller than I prime. Okay? So again, the different flavors of this formula, different encodings have been studied for different proof systems. We'll focus today on resolution size already there. So what we will see is that Haken in 1987 gave a linear, exponential lower bound, so exponential in linear in n. And this is tight for the pigeonhole principle. So Buss and Pitassi proved that actually you can do big exponential in big O of n. However, if m is ridiculously large, like if m is something like exponential in n log n, actually I think square root n log n, then you can actually do slightly better. Then you can do a lower bound that is exponential in square root n log n. Okay. And then there's a sequence of works by Raz and Razborov, 4 works. So the journal version of Raz is from 2008. And then there are 3 Razborov papers from 2001, 2003, 2004, that actually not only for vanilla, but for all versions of the pigeonhole principle that you saw, there's a lower bound that is exponential in the cube root of n. And we don't know if the square root or the cube root is the right bound. And this is one of the questions, one of Alexander Razborov's favorite questions that he has on his big open problems in proof complexity list.
So the implication for m larger than square root n log n, that's like Buss and Pitassi, or?
Yes, so Buss and Pitassi give the upper bound, and then they show that in fact if m gets ridiculously large, then you can do slightly better. Basically, you can get down from exponential in n to exponential in a little bit more than square root n. Yes, that's Buss and Pitassi. The weak pigeonhole principle in general is typically that's when m is much larger than n. What does much mean? Well, typically a good definition of weak is to say, that m is, say, larger than m squared, because that's typically where the techniques, in fact, where the techniques we'll see today break down. And we still know, for these results here, we still have strong lower bounds for resolution, but for polynomial calculus that we talked about in the first lecture, we have nothing for the weak pigeonhole principle. So that's a big open problem. But what we will show today, and maybe I'll just write it over here so that we remember. So this is due to Haken in 85. So the resolution length lower bound or size lower bound for pigeonhole principle with n plus 1 pigeons in n holes, we have exponential in n. So this is what we're going to prove today. And it's worth noting that in terms of formula size, the lower bound then becomes actually big omega of cube root of n, because the size of the pigeonhole principle formula scales like n cubed, and that's because of all the whole axioms. There are a cubic number of whole axioms. And it's not so hard to show that for any formula of size capital N, there is a resolution refutation in at most exponential in capital N. And then you can ask, like, what's the right bound? And we will see in future lectures where we actually get tight lower bounds that are linear in the formula size, not a cube root of formula size, but actually linear. But for pigeonhole principle, this is tight. So we will follow Pudlak's exposition. I think I'll get rid of these lower bounds now. And Pudlak says, well, if we want to think about resolution, let's think about it as a game played between a prosecutor and a defendant. And the game is played on an unsatisfiable CNF formula F. And the defendant claims that the formula is in fact satisfiable, so the defendant has a satisfying assignment, or so he says. And the prosecutor tries to get the defendant convicted of lying. And in every round, the prosecutor asks the defendant about the value of a variable, and the defendant answers. Every once in a while, the prosecutor forgets values. We'll get to that in a second, why the prosecutor would do that. And then this is a game of full information. So if a value has been asked and the defendant gave one answer, then the prosecutor forgets. The defendant knows this. When he gets the question again, he might answer completely differently because everybody has forgotten what the value was. Okay? And the prosecutor wins, a winning position. So the prosecutor writes down the partial assignment of the variables asked for and not forgotten. So every position in the game is a partial truth value assignment, and a winning position is when the partial truth value assignment violates a clause in the input formula, so when it violates an axiom. More formally, so the game is in each round, the prosecutor decides what the move is. So the prosecutor either does ask of X. Okay, so the prosecutor has a record R, which is a partial truth value assignment. And initially, this is the empty truth value assignment. And the prosecutor can ask for a variable. Defendant then answers that X is equal to B, a bit in 0, 1. And the record is then extended to R union X is equal to B. Okay? Or the prosecutor can forget and get a new record R prime that is a strict subset of R. In which case, everybody involved knows that the new record is R prime. As we said, a winning position is a record that violates a clause in F, which is also a formula that both prosecutor and defendant know. A prosecutor's strategy is a collection of records with associated moves that wins against any defendant. Okay, so a prosecutor's strategy is a deterministic strategy. The prosecutor will just ask, and regardless of how the defendant answers, sooner or later we reach a winning position. The complexity measures that we're interested in are, for a strategy, is the number of records. Actually, let me number of records, the maximum size of a record, and the maximum number of rounds. Okay, in the prosecutor-defendant game. And the reason we care about this is that the prosecutor-defendant game is just resolution in disguise. Okay? So if I have a resolution refutation, in length or size L, in width W, and in depth D, which is, recall, is the longest path in a diag, then this will give me a prosecutor strategy with at most 2 L records, with width at most W plus 1, and with at most 2 D rounds. And in the other direction, is this still visible, by the way, for the...
Yes.
And in the other direction, see if I can write this here, if there is a prosecutor strategy, number of records S, and max size, let's say K, and number of rounds, max number of rounds required for any clay, R, then that actually gives me a resolution refutation in length at most S, in width at most K, and in depth at most R. Okay, so if I want to understand resolution, I can focus on prosecutor-defendant games, and this is what we will do today. And somehow this means that if I want to come up with good upper bounds, I can focus on prosecutor strategies. If I want to prove lower bounds, then I need good defendant strategies. Okay. This connection is written down more clearly in the notes, and we need a proof why this is true. That proof is also in the notes, and it will be in the beautiful scribe notes. Let me, just in order to save time, let me in fact do the proof by picture. Okay, so suppose here is a formula of 5 clauses. This is an axiom clause, X or Z. Let's say that not Y or not Z is the clause. Let's say that Y or Z is an axiom clause. Let's say that Y or not Z is also an axiom clause. And let's say that not X or not Y is an input clause. So let me now do a resolution refutation. Let me resolve these two to get Y. Let me resolve these two to get X or not Y. Then let me resolve X or not Y with Y to get X. Let me resolve Y with not X or not Y to get not X. And let me resolve X and not X to get contradiction. The claim is now that this is basically a prosecutor strategy. Okay? So let's just, again, this is kind of proof by example, but basically the idea is that we start at the end of the proof contradiction, and the invariant that I'll maintain as prosecutor is that I will have a minimal assignment that falsifies the clause that I'm at. Okay, which I'm in good shape. We're starting with the empty assignment. The empty assignment definitely falsifies the empty clause. That's nice. Okay, now what I do next is I ask about the value of the variable resolved over to get here, that's x. Suppose that the defendant says x false, then I move to the clause x. If the defendant would have said true, I move to the clause not x. Okay? And then I minimize the assignment so that I only falsify exactly this clause, except I don't need to do anything here. But suppose now, for instance, that here I should ask for y, because that's the variable resolved over to get here. Now suppose that the defendant says that y is false. Then I move here. Now I'm falsifying the clause y, but I no longer need x. So here I issue a forget move to forget x. And now my truth value assignment is y. And now I will ask about z. And regardless of what the defendant answers, I will go to an input clause. And so I have a winning position, an assignment that violates an input clause. And it's kind of clear that I'm picking up 2 records per step. So the depth will be at most 2 times, the number of rounds will be at most 2 times the depth. In fact, the number of rounds, the depth corresponds to the number of non-forgetting steps, right? And it's clear that the width is at most the clause that I'm at, plus potentially 1 extra literal to ask where to go next. And the size of, since I'm always forgetting so that I'm uniquely identifying the node where I am, the number of records in the strategy will be 2 times, at most 2 times the number of clauses in the refutation. So this is a proof by picture. Are people happy with this? Okay. And I won't do the other direction. The other direction is slightly trickier, but the other direction is also true. Basically, you take any prosecutor strategy and you realize it has to have some kind of DAG-like structure. You extract that DAG-like structure. You argue that it has to be a resolution refutation. Okay, obviously, you need to fill in the details, but that's how it goes. I should say something that might come in handy later. If you want to capture tree-like resolution, then this is this game, except you never have any forget moves. That's tree-like resolution. From this correspondence, you immediately, by the way, also get the upper bound that I talked about. That you will see now that clearly there's always a strategy that uses at most n rounds, where n is the number of variables. And if you only have n rounds, then you will have at most 2 to the n, essentially, records. So that shows that you can always find the resolution refutation, even a tree-like resolution refutation, in exponential size and linear depth.
How did it take so long to get the upper bound? I think we saw it was 97.
Oh, because note that would give us, for pigeonhole principle, that would give us exponentially in n squared. But I'm claiming exponentially in n. So actually, Bus and Pitassi are.
Okay.
So there are different ends. That's tricky. That's a good question. Thank you. I should have mentioned that. So again, to point out, like, if it's so easy, why was there a citation even for the pigeonhole principle exponentially in an upper bound? Well, because the n in the pigeonhole principle is not the number of variables, it's the number of holes. And with n holes and n plus 1 pigeons, the number of variables is actually n times n plus 1, which is n squared, essentially. And what Bus and Pitassi showed is that you actually don't need n squared, you can get down to n.
So it's always the number of pigeons that the upper bound cares about, not the floor representing.
Typically, the number of holes is always smaller than the number of pigeons, because otherwise it's kind of hard to refute it. And yes, then you care about how, like, it gets easier if you get a ridiculous number. I mean, the more pigeons you add, the more over-constrained it gets.
Okay.
And what Bus and Pitassi showed, like, if it gets ridiculously over-constrained, if I'm saying that an exponential number of pigeons truly have to fit in these holes, then it gets slightly easier for resolution to figure out how bizarre this claim is. Stronger proof systems will figure this out faster. I'm a little bit out of my comfort zone now, but I think, like, if you go already bounded depth, Frege can figure out, I think, that 2 n pigeons don't fit into n holes. Bounded depth Frege also has a problem to count, and we didn't even define it, so this is a slight detour, but it's basically bounded depth Frege is resolution, except that you have now not just clauses, but any formulas of bounded depth, and the rules are kind of the same. The pigeonhole principle with n+1 pigeons and n holes is still hard, but approximately counting gets slightly easier. Okay, so what we're gonna do now is we're gonna find the erasure. Are we happy with, do we remember the pigeonhole principle? Because then I'm going to erase it. Any questions while I clear the board? Otherwise, I'll just say, so basically now if we believe that the prosecutor-defendant game is the same as resolution, and I sort of, again, we did, by picture, we did actually the direction that we need. The only direction that we need is that a short resolution refutation will give us a prosecutor strategy with few records. So what we will prove as a law, and this is already the third lemma because lemma 2 was my proof by picture. So lemma 3 says that there exists a positive constant delta such that prosecutor requires at least 2 to the delta n records when we're playing on the pigeonhole principle with n+1 pigeons and n holes, and this assumes that n is large enough. So for a large enough n, the number of records that the prosecutor needs scales exponentially. If we can prove this, then we can go home. Is this clear? Okay, so let's see how fast we can prove this. So basically, again, what do I need to do? I need to come up with a defendant strategy that shows that the prosecutor needs many records. Now, note that I can't just do this with one round of play. Like if they play the game once, then prosecutor only needs to visit a linear number of records, pretty much. Okay, and if they play the game twice, then they need 2 times linear. So the way to think about this is we might play the game over and over again. And as a defendant, so we are now the defendant from now on. We're like the good guys, the lower bound guys. We believe in I don't know, judicial reform, maybe. No, people shouldn't be convicted just because they're reasoning badly about logic formulas. So we need to argue that if we play this game over and over again, we will force and if the prosecutor can always win, the only way the prosecutor can do so is to have an exponential number of records. Okay. So how would we do this? So with randomization, so here's the defendant strategy. So before every round of play, uniformly at random, I just send n/4 pigeons to n/4 holes, uniformly and independently at random. And now, by the way, this is the kind of thing that we will always do from now on. So in order for this argument to work, I'm assuming that n is always divisible by 4. Hopefully this is not a big deal. I mean, if n would happen not to be divisible by 4, we would fix it. But let's just assume that also, in fact, if we get a lower bound for every 4th n, that's good enough, but there are also other fixes. So we're typically like actually lying to, so from now on, for the rest of this proof, every positive integer is divisible by 4. You're happy with this? Okay, good. Excellent. Now let M be this partial matching. Actually, let me be slightly more careful. We will have a matching, we will carry it with us. So when I want to be super careful, let me refer to this initial matching as M init, except that at some point I will run out of energy and it will be clear from context when I mean the initial M and when I mean an M that we will grow later. But I'll try to write, let's see, I'll try to write M init for as long as I can. Okay. Now, this is a matching from pigeons to holes, and we are actually dealing with a Boolean formula, but hopefully you can agree with me that given any matching M, I can actually define, there's sort of one-to-one correspondence between matchings and partial truth value assignments in the following way. Oops. Given any matching M, I can define a row M, which is defined in the following way. So it sets xij to true, to 1, if ij happens to be in the matching. It sets xij to false if I is in the matching, but with some j prime that is not j. And otherwise, xij is unassigned, which we'll write with star. Okay, so it's clear that for any matching, I can define a truth value assignment like this that basically corresponds to the matching. So I'll go back and forth between row and M. Maybe I'll even mix them up on the board, but you will know what I mean. Okay? And now this is the game. Row is what we're playing. So some terminology. So I will always, defendant will always maintain at all times a matching that is always, is always a super matching of M init. Okay? So as I'm answering prosecutor questions, I'm going to grow my matching. Okay, and then let me have two more pieces of terminology. Let's say that a pigeon I is assigned in a record R if xij equals 1 is in the record. Let's say that j is, both I and j, both the pigeon I and the whole j are assigned in a record if there's a pigeon I going to whole j. Okay? The whole j is prohibited in R for I if xij false is in the record. Okay? So the prosecutor knows that pigeon I is not flying into that hole. Okay? Just a piece of terminology. So now, what's the defendant strategy? At all times, I maintain my matching, and I will answer according to that matching. So if there's an ask about xij, then there are two cases. If I is in the domain of the matching I have right now, then I just answer truthfully by row xij. Row is this guy. So this should be row M, I guess. Okay? Because I have already committed to where the pigeon is going, so I just tell. Note, by the way, that this will always happen for my random choices. So there are n over 4 random choices for which the prosecutor could very cheaply get information, except that the prosecutor has no way of knowing my random choices. Note that it's important that the prosecutor committed to his strategy first, and I'm making my random choice every time. Okay? Otherwise, if I is not in the domain of M, what should I do? And I just say no. No, pigeon is not going into that hole. That seems like a safe choice. I mean, committing to pigeon actually going to a hole, that's like revealing a lot of information. Just saying that the pigeon doesn't go there, that's somehow, I'm kicking the can down the road. Once I've done this, I check if there are now at least n/2 prohibited holes for pigeon I. If so, I reserve a free J star. Okay, what does this mean? Well, obviously, I can't pick a J star. I can't pick a J star that is for which the prosecutor knows that I doesn't go to J star. Obviously, also, if some other pigeon already went to J star, then I'm not picking that hole. But otherwise, let's say I pick the smallest J star such that it's not prohibited on the record, and no other pigeon is going to that whole J star. And then I extend M with I being sent to J star.
So you try 1, 2, and then if you are in near, then you reserve, or?
So
Okay.
we
don't have any more.
We're back after that, just to create some more suspense, because this is really the key part of the proof. So let's see, where were we? So again, so I now, what did the defendant do? The defendant committed to a random partial matching of n/4 pigeons to n/4 holes. And then it's maintaining a matching M at all times. It's if a pigeon is already in the domain of the matching, then I answer accordingly. If the prosecutor is asking about that pigeon I and the hole that it's actually going to, then I say yes. If it's asking about that pigeon I and some other hole, I say no. If it's asking about some pigeon for which I'm not yet committed in M, I say no. That's a safe answer.
Yeah, I say no, but I'm overly constrained. I research, but I don't.
But now I check, like, oh, I'm actually getting a bit nervous here, because now apparently, like, the prosecutor has already ruled out over half of the holes. I'm getting a little bit constrained now. I'd better think ahead and reserve a hole. Okay. Obviously, the prosecutor doesn't know this, but I know this now, and I've reserved J star, and I grew my matching. So from now on, I will play. If I get a question about that pigeon again, I have fully committed to what to do. Make sense? Okay.
Is that J star you also choose uniformly at random, or?
It doesn't really matter. I chose it to be like the smallest legitimate choice, say. It's deterministic at this point.
Okay.
Yeah. If there's a forget move, then obviously I don't need to answer anything, but I can check for all pigeons, or if, do I find the pigeon I which is such that I is not assigned in the record? Like, the prosecutor has not nailed down exactly where this pigeon is flying. And there are also strictly less than n/2 prohibited holes. Both of this is in the current record R after forgetting. So I guess this is R prime. Then for every such pigeon, I just remove I in my match. Okay, I had reserved, but now I looks very unconstrained again, so I decommit. Unless the prosecutor has figured out exactly where the pigeon goes and like knows my choice, then I stick with it. Okay, does it make sense? Okay, so I claim we're done now. Now we just now we just need to analyze why this shows that when I'm playing according to this strategy, prosecutor will need a exponential number of records to win against me. Okay, how are we doing on time? Not too bad. I thought it would be worse. Okay. Let's say that a pigeon I, actually let me maybe set it over here because I want to change it. Let's say that a pigeon I is thoroughly examined in R if one or two things hold. Either xij equals 1 is in R, so the prosecutor knows exactly where the pigeon is, or xij is 0 for at least n over 2 holes. Okay? Basically, a pigeon I is thoroughly examined if the prosecutor knows a lot about this pigeon. The prosecutor has done non-trivial progress in pinning down this pigeon. Okay? Let me say that a record R is informative. It's an interesting record. It's an informative record if it contains at least n over 4 thoroughly examined pigeons. Okay? Do we remember what the sign and prohibited means? I think I'm going to clear this board now, except for the lemma that we're proving. Okay, because now my claim is the following, or Pavel Pulak's claim really, is that this is going to be lemma 4. Before a prosecutor win, in any game of play, we will pass through, we will see an informative record. There is no way for the prosecutor to win except during play an informative record will be generated. Right? Does the claim make sense? Okay. So the observation is that as long as the prosecutor is asking and forgetting and the defendant plays according to the strategy, there is no contradiction. There is no way the defendant can lose as long as it's playing this, because it's just playing partial matchings. Okay, so how does the defendant lose that? The only thing that can fail is that we cannot reserve a free hole. Okay, and I didn't tell you what happens then. Well, let's say, if this fails, then we just give up. And this is the only thing. So the game ends when we realize that there's a somewhat constrained pigeon. Now I need to reserve a hole J star, and I don't find any. And then the defendant just breaks down in tears and says, I was lying all along. Okay, sorry, you got me. Okay, so when does this happen? Well, there are exactly n over 2 prohibited holes. That's why we triggered the reserve step. Okay, and I'm not able to reserve any other hole, so that means that actually all those other holes are taken. Okay, so this means that basically reserve J star after 2 is what fails. But that means that the domain of our current matching is at least n over 2, because there are at most n over 2 prohibited holes, but all other holes are apparently busy already. Okay, but that means, if you think about it, that domain of M minus the initial domain is at least n over 4. Right? Because n over 4 of these pigeons are just the initial commits. And those don't need any justification, but apparently there are n over 4 more. Okay, why do these pigeons have holes reserved in M? Why have I reserved holes for these pigeons? Well, either because they have at least n over 2 prohibited holes, or they've actually been assigned a concrete hole. Otherwise, I would have decommitted, right? But that's exactly what a thoroughly examined pigeon is. And we see here that we must have, since the domain size is n over 4, there are at least n over 4 thoroughly examined pigeons, which is what an informative record is. This is a key step. Does this make sense? Should I say this again?
So, question in the definition of thoroughly examined, is this an or, either A or B, or is it M?
It's an or.
Okay. Yeah.
There are ors, like, yeah. But this here, like this is the negation of this, right? So this is an or, and here it's an and. Like I decommit if neither of this holds. And hence, since these guys are in the matching, either this or this must have, not hold. Now, are we happy with lemma 4? Okay. But now,
there's a question at bar.
Yes.
Yes. So the question is, why is this an or in the thoroughly examined? If in order to have had something assigned that was in the initial domain, you had to get zeros at n over 2 things. What is the situation where this is assigned 1?
Oh, because the prosecutor kept asking. The prosecutor went all in on that pigeon and asked about all the holes and figured out which hole I was thinking about and then forgot everything else.
I forgot it. Okay, thank you.
Make sense?
Yeah.
Or maybe, yeah, so there are like 2 reasons why once I've reserved the whole J star, then, the prosecutor keeps asking about that pigeon, and by luck or by exhaustive search, will hit J star sooner or later. And then, of course, once you as if you're a prosecutor, then having a 1 is kind of a nice thing, right? Then you know exactly where the pigeon goes. So I would kind of keep it. But it's really, we don't care what the prosecutor does. We're just, we're considering a pigeon to be constrained if either the prosecutor knows exactly where it goes or has ruled out at least half of the holes. Okay, so now we're almost done. So the punchline of this is going to be, okay, so an informative record is constraining lots and lots of pigeons. Okay? And I know that in any round of this game, not a thing like in any play of this game, I'm passing through an informative record. Okay? But note that my initial matching of n over 4 pigeon to n over 4 holes also contains lots of information. In fact, so much information that any given random initial matching is very unlikely to be consistent with any particular informative record. Therefore, there has to be lots of informative records. Let me write that down. Okay, but basically, we're on the home stretch now. We just need to do the math. Okay. So what I've want to prove, let's see, are we done with, I think we're done with this now. We know that records are informative, so we don't need to remember the strategy any longer. So what I want to say is for any fixed informative R, I'm going to say I want to prove that the probability over my random matching that the game passes through R is very small, exponentially small. In fact, I'm going to prove something slightly stronger. I'm going to prove even the probability that M is consistent with R in the first place. Which is a necessary condition for us being able to pass through R, but not sufficient. So the probability that M is consistent with R again is going to be exponentially small. So it's going to be something like, we're going to prove that it's 2 to the, I don't know, 2 to the minus delta n for some positive delta. Okay? Suppose we can do this, then I claim we're home. Okay? Because, why? Well, because we're passing through some informative record with 100% probability. So 100% is equal to the probability over M that there exists an informative R that is consistent with M. Right? Now, by the union bound, I can just sum over all informative R and say, what's the probability for this fixed informative record that M and R are consistent? What do I mean by consistent? Well, they're clearly not, if they have inconsistent opinions about the pigeon, then that's inconsistent. Okay. Now I claim that this is exponentially small. Suppose that this is true, like let's call this star maybe. And then here we get by star. I would now get that, okay, so this is not an equality, this is a less than equal. So this is then less equal number of informative R times 2 to the minus delta n. Okay, but if number of informative records times 2 to the minus delta n is larger than 1, that tells us that the number of informative R is 2 to the positive delta n. Very good. So all I need to do now, this is a so-called bottleneck counting argument. I've pinned down interesting records, and because they are so interesting, because they are so informative, the probability that I hit any particular such record is very small. But if there were few records, I would need to hit them pretty often in order to sum up to probability 1. And this is a contradiction. Hence, there has to be many records. Okay? So now, what do we do now? Are we happy with this? Because then I think I might clear actually all of the board now. Because now we just need to prove that a partial matching is unlikely to be consistent with an informative record. And then we can go home. Okay. So take your informative records and just write capital A sub R for the thoroughly, I can spell, thoroughly investigated pigeons in R. Okay, let's just warm up. Over random matching, what is the kind of intersection I expect between the domain of my initial matching and the informative record? Well, there are at least n over 4 thoroughly examined pigeons. I'm picking exactly n over 4 pigeons here. So basically, just look at a single pigeon. What is the probability that it is one of the thoroughly investigated one? It's a quarter, right? Okay, and I'm doing this n over 4 times. So I'm expecting to get something like n over 16. In fact, there's an extra pigeon, so I get a slight greater equality. In expectation. How many will I actually get? Note that this is a random choice. Okay, arguing, and this is where we get to the point where it's getting late in the day and we don't want to do calculations. So I'll just hand wave to you and then I'll show you the calculation, but you'll have to do it. Okay, but basically, look at a single pigeon. Intuitively, I'm flipping a coin with probability a quarter of ending up in the thoroughly investigated pigeons. And I'm doing this a linear number of times. Now, if I flip a coin like a linear number of times with probability a quarter of getting heads, then I will get a quarter of heads. Maybe not exactly a quarter, but it will be sharply concentrated around the quarter, right? If I have a fair coin and flip it 1,000 times, then I will get 500 heads plus minus the standard deviation. But it won't be like 300 or 700, definitely. It will be, somewhere between 450 and 550 or so. This is concentration of measure, and this is what happens here. So I won't get n over 16, but except with exponentially small probability, the intersection will be at least half of this. Definitely. Okay. There's no way, except with exponential, it would be like a truly outrageously improbable event. Okay. Well, that's the intuitive argument.
The expectation is over m, but m units in m are the same. You just sample them.
Yeah, sorry. Yeah. And then I'm a little bit sloppy here because now it's like here's the random variable, and I guess here it's the sample. So it's like, okay, I could do m sampled according to the fancy, but maybe you weren't worried about this. I'm sort of overloading the sample and the random variable. Okay. So actually, let me just write down the probability that the intersection is way smaller than I expect, like the probability that is at most n over 32, say, is exactly, well, let's just count the number of ways that can happen. Well, the way this can happen is that for some weird reason, from this set of informative pigeons, I only picked I for I at most n over 32. And then all the other pigeons are picked from the complement set. Okay. These are the number of ways I can pick pigeons in order not to hit the informative set. And the total number of ways to pick is obviously n plus 1, choose n over 4. Okay, and now you just do the math. Basically, we can estimate these. You need to be a little bit careful. Basically, you need to use Stirling's formula to estimate how large these things are. And then you take a deep breath and you work out the math. And there's some pain involved. And then you get something like, 2 to the minus delta prime n for a positive delta prime. If you've seen these calculations before, then great, nothing fun will happen. If you've never seen this kind of thing before, then actually do the calculation once, just to see how concentrational measure works. And the scribe notes will contain details about this, but there's nothing. Basically, we need to estimate how large these things are, and you just plug in the estimates, and then off you go. Yeah. Okay, so that means that except with exponentially small probability, the intersection is in fact fairly large. It's like at least n over 32 pigeons. Okay, so good. So now suppose that in fact the intersection is then at least n over 32. For every I in this intersection, we have one or two cases. We know that R is doing one of two things. It either specifies a J such that I has to be sent exactly to J, or B, it prohibits n over 2 case for I. Okay? And now the point is, without loss of duality, in our head, let's just think about how these pigeons in the intersection are being chosen. Let's choose them one by one in M. Okay, in M in it. And then you see that for the I plus first pigeon, chosen in M init and in this intersection, what probability do we get here? Probability to be consistent is, well, I mean, there's exactly one hole to choose from. If everything has gone well so far, there's a total of n. I mean, you've picked I pigeons already, and now you're picking the I plus first. This is how many holes you can choose randomly. Only one is good. This is the probability that you hit exactly that hole. Okay? What's the probability that you're consistent with all the prohibited holes? Well, potentially there are n over 2. There are at most n over 2 holes that are good. And again, you're choosing between n minus I holes. So this is the probability to be consistent. Now, I don't know how many pigeons are of type A and how many pigeons are of type B, but I know in both cases, if you just do the math, this is way less than 2/3 because I is less than n over 32. So basically, I can plug in here n I mean, I can minimize and take n minus n over 32, and then just do the math. And I mean, 2/3 is like a ridiculous block. Okay. Now this means that total probability of being consistent is then, well, at most 2/3 every time. How many times am I doing this? Well, at least n over 32. And then you just pick some delta so that this is at most 2 to the minus delta double prime n, or some delta double prime that is positive. Okay, and now we're actually done. Because putting things together, the probability that M and R are consistent, that probability is less than the probability that IR intersection the domain of M, that this is small, that is less than n over 32, plus the probability over M that the intersection is actually large, but M is consistent with R. And we've seen that, well, the probability that the intersection is small is exponentially small. And if the intersection is large, then it's extremely unlikely that we have something consistent. And now you just, pick delta large enough or small enough, but still positive, so that 2 to the minus delta n is smaller than these two guys. And note now that this is where in concentrational measure, and also here, we're just, we're being lazy, just pick n large enough. But I think, if you optimize parameters, then you don't have to pick any ridiculous values. I think this kicks in pretty soon. So, okay, but this proves actually, now we've proven lemma 3. And this, as we argued before, proves the pigeonhole principle n plus 1 n lower bound. We're done. With some friendly slack again. We didn't clock in exactly at 2 hours, but 2 hours plus a bit, including breaks. So what did I cheat you on? Nothing really. This is the proof. I didn't do this calculation, but again, I think this is Stirling's formula, and then just or ask mathematical people to do it. Maybe I don't know if they will, but hopefully. ChatGPT, I'm sure, would happily oblige to prove anything you want. Whether it would make sense is then you can ask it to prove the opposite, and it will probably do that as well. I actually asked ChatGPT about this. I wanted to have this reference for this xn upper bound, and I asked ChatGPT, and it said it follows trivially because for any formula, exponentially in n is an upper bound. So it made it, it's so n, and it said, well, exponentially n is an upper bound. And then we had a discussion, and I tried to convince it that no. And it said also exponentially n actually holds also for tree-like resolution, which is also wrong because I didn't say that. But for tree-like resolution, the lower bound is actually 2 to the n log n. So like for tree-like resolution, actually the lower bound is n factorial, asymptotically n factorial, whereas general resolution is just 2 to the n. Okay, so general resolution is slightly better. So I didn't do this calculation. I didn't do the equivalence between the prosecutor-defendant game and resolution, but we sort of did the proof by picture. The direction that we need is what we did, exactly what I told you about. The other direction that is nice to have, that they're in fact exactly the same game, is something that we will use later in the course. I'm not sure whether we will do that or if I'll just give it to you as an exercise. But again, it's not hard. Some of you will have seen this exercise in other contexts when talking to me. And apart from this is it. I mean, this is the lower bound. So, questions before we call it a day?
So in some sense, is it like we are arguing that there exists some very good initial matching that the delayer could hardwire and make this a strategy? Like, is that... Yeah. Like there exists such a matching that
No. Well, okay, what are we doing? So this is a slightly, for those of you who know some proof complexity, so the slightly weird thing here is that one way of phrasing this is we're doing a random restriction argument, except I'm actually going to try to do most of the standard resolution lower bounds without random restrictions, and we'll see random restrictions later. Because I think it's helpful to think about it this way for some of the lower bounds that we don't know how to prove and that we don't seem to be able to prove with random restrictions. So I don't want us to pollute our minds. Okay, but I don't think it's the case that you could sort of commit to the random restriction ahead of time. But one way, I guess the way Haken proved it, I think, is like one equivalent way of phrasing this is, and this is how the random restriction argument goes. So you need a number of things that we didn't talk about. So you need to say that, well, if I have a CNF formula and I have a resolution refutation, and I pick some variables and set them to values, and I just propagate this through the whole proof and the whole formula, then I actually get the simplified, restricted sequence of clauses in the proof will be a valid resolution proof for the simplified formula, modulo some massaging, which is not hard to do. So one way of phrasing what we've seen today would be to say, okay, I start with n plus 1 pigeons and n holes. Now I hit it with a random restriction that sends like a linear number of pigeons to holes. And I look at that formula, and now I see that that restricted proof will not contain any very large clauses, because very large clauses will just be satisfied and vanish by my random restriction. Okay, but now by a separate argument, I prove that, well, I don't know anything about size, but I do know that any resolution refutation of a pigeonhole principal formula has large clauses. Okay, and in fact, this restricted formula with the restricted proof is still a pigeonhole principle over slightly fewer pigeons, but it's still a pigeonhole principal formula. And very interestingly, if the original pigeonhole principle was short, so I had a short proof, then by just a union bounding argument, I now have a refutation of a slightly smaller pigeonhole principal formula without any large clauses. And here I could do a counting argument and like hardwire the random restriction. But the way it's in order for the random restriction argument to work, you somehow, so sort of mentally you have to fix the refutation first. So we have to fix the prosecutor strategy first. Right. And then choose the random restriction. What wouldn't have worked here at all is if I tell the prosecutor, by the way, I've committed to a random truth value assignment that I will use in all the games that we play. Because then the prosecutor would just spend, some time to figure out exactly what my matching is, and then would just play accordingly. So it is like this lower bound would not work if defendant committed to the random matching before prosecutor. It's very important that the prosecutor goes first, commits to a strategy, and now only then does defendant do a random matching and play.
Right.
More questions?
I guess also from a game theoretic perspective is kind of, you can assume that the prosecutor knows the defendant's strategy, except for sort of like something that's explicitly random, because this is something that is explicitly only done after the game started, like at the start of the game. But other choices like the fact that after a half of the holes are set, the defendant commits to a hole and how, that we can assume that the prosecutor knows this because there is sort of...
Well, yes and no. In fact, we cannot assume this in the sense that the prosecutor has a resolution proof. Right? It should be a valid proof. And that exists regardless of what the defendant is doing. However, you're right that in the sense of when we want to leverage our lower bound techniques, then I don't know how to do any lower bound techniques where the prosecutor doesn't know exactly how the defendant will play. Because we're not analyzing, if you think about what we're doing, we're actually not analyzing, we never used anywhere that the prosecutor has a complete strategy. We're just using that the prosecutor is able to win against the defendant. So once the prosecutor knows sort of, in our proof, what the defendant will do, we can sort of only use that the prosecutor will win against that defendant. But that is a weakness in our lower bound technique. Because actually the prosecutor has to commit ahead of time before the defendant even does anything. But I don't know how to make use of that. And that is, in fact, in some sense, maybe that's one of the difficulties in the lower bounds that are harder. Because it's a good, I mean, it's important to note that we're not only lower bounding resolution proofs, we're lower bounding the size of any strategy that wins against a defendant that plays like this. And you don't need the complete resolution proof to win against a defendant like this, necessarily.
There's also a question in Copenhagen.
Say again, sorry?
We have a question over here.
No, not really a question, but in your second binomial coefficient, do you want n over 4 minus I?
Where are we here somewhere?
Yes, the second one above.
I think I want to choose I, guys, from the informative.
Yes. And then one
And
next
the
to it.
remaining N. Oh, yes. Thank you. I wonder if this is a typo in my notes also. Thank you. Yes, that's super wrong. Thanks a lot. Yes. In fact, my notes are correct. Thank you. Yes, N over 4, yes. So I make I choices from choices from here, and the remaining N over 4 minus I choices over here. Yes, thank you so much. Otherwise, the calculations would, the lower bound would become a bit more challenging, I think. More questions, comments, or corrections?
There's another question from Copenhagen. It's on this set IR. So my question was, it seemed like during your argument you assumed that an element is in IR essentially uniformly at random. And I guess my question about this is what I was questioning this as it seems like
absolutely not true. That's absolutely not true. This is adversarial. You don't know anything about R.
Okay.
So all of the R is fixed. This is very important. R is fixed. All the randomness is in M. Very important. Thank you for the question. Extremely important point. I have no control over R. So, but the only thing I do know is that before prosecutor wins, we're passing through some informative R. I have no control over that. It's very non-random. I mean, it's given by the prosecutor strategy. It's highly non-random. It's highly adversarial. The only control I have as a defendant is my random initial assignment, my random initial matching M in it. That's the only randomness. Everything you see here over R is fixed. The randomness is only over M. Does that make sense?
So then are you saying that the random M is consistent with R? Because it seems like R would depend on M, if I'm not mistaken.
No. R is fixed. Right? R, all you know about R, this is very important. All you know about R is that there is at least n over 4 pigeons that are thoroughly investigated, thoroughly examined. What does that mean? That in the record R for a thoroughly investigated pigeon I, either the record specifies exactly where the pigeon goes to a particular hole, or it rules out half of the holes. I don't know which is the case. Like, I don't know how many pigeons are pinned down exactly to holes and for how many pigeons I'm just ruling out half of the holes. I have no idea. I have no idea what these pigeons are. All I know about R is that there are n over 4 such pigeons for which the record contains lots of information. Which these pigeons are, whether they are mapped to holes or whether they have lots of holes ruled out, all of that is adversarial. I have no control. All I know is M is random. And that's why in my probabilities, I'm doing a case analysis for every pigeon. I know that every pigeon in IR is either of type A or type B, but I don't know. Does this make sense?
Yes.
It's a very important point that I have no control over R. It would be great if R was random, but it isn't. So it's only the initial random matching M in it, curly M in it, that is chosen by the defendant. That's the only source of randomness. Everything else is fully deterministic. And this is also connecting to this question. When I'm enlarging my matching with these new J stars, we discussed whether they were random choices or not. And I said, no, they're not. They're deterministic because I don't know how to use that randomness anyway. So like everything is fully deterministic except the initial choice of n over 4 pigeons sent at random uniformly to n over 4 holes. That's the only source of randomness. Any final question before we call it a day?
Yeah, maybe about the construction of the records from the resolution back. So you said that if you have if you have L nodes in the tree, then or in the DAC, then you can make 2 L records.
Yes.
So I was thinking you have a node corresponding to a record corresponding to the node, but that exactly specifies that clause, and then you have, like, in 2 directions you have one that extends that by 1 literal.
Correct.
So they will have 3 L.
I'm charging those to the node below.
Okay, but then you could, if that node has a large, so I have to argue about the number of edges in the DAG?
No, I'm just charging all the. I mean, firstly, I would be so super happy with 3 times L. If that makes you happier, then I'm happy with 3. But you can always charge to the node at the other side of the edge. So contradiction doesn't get charged for anything. And then for the resolution steps, so you have C or D here, and you have C or X, and then you have D or not X. Okay. And my records, there is going to be the record here that is a minimal assignment that falsifies C or D. Here I'm going to have a record minimal assignment that falsifies C or X. Here I'm going to have a minimal assignment that falsifies D or not X. And then, as I said, here we actually have the assignment that falsifies C or D or X, right? And here we have the assignment, oops, I'm confused. the assignment that falsifies C or D or not X, right? And those I'm going to charge down here.
But a node could have a large out degree, right?
Oh, is that a problem? We need a factor 3 after all. Maybe we need to think about it offline. That's a good question. I'm happy with a 3. I thought we had a 2. But now you're making me... Good question. I mean, the point is what we're worried about, that this guy is being resolved in many directions, and it's a little bit... Yeah, so we can definitely get a 3. Can we get a 2? I don't know. I'm happy with a 3. Maybe we'll have to think about it and then fix it to be we can definitely let's say 3 for now, and then let's see if we can get back a 2 by some thinking. But it might. Good question. Good catch. Thank you. Okay, so let's call it a day.